Now, when we talk about electric circuits, one of the main things that we have to deal with is the idea of electric power. Electric power is the idea that electricity, the main use of it is transferring energy from one place to another, or transferring types of energy from one form to another. So for an example, let's say you have just a very simple setup. You have a waterfall. Waterfall, you have potential energy of the water turns into kinetic energy as it falls. You turn a water wheel, and that spins an electric generator. An electric generator, we're not going to cover very much in this class, but it's the idea that you have loops of wire around magnets, or magnets around loops of wire, and then as it spins, you create an electric charge. The same thing for an electric motor, it's just one is an input and one is an output. The generator, some form of energy causes it to rotate, which gives energy in the form of a voltage and in form of an electric potential difference to those electric charges. So that causes them to flow. It gives them energy that then gets used up in the electric motor, and then the charges return to the generator to repeat the process over and over again. So we have that kind of circuit. It has to have that circuit approach. Then if we talk about how do we deal with that mathematically, well, the idea is energy is charge times electric potential difference, because electric potential difference, if you remember, is measured in volts, which are joules per coulomb. So if we want to know how much energy we've used, we need to figure out how much electric charge multiplied by how much voltage, or how much electric potential difference is supplied. So that gives us energy, because it's joules per coulomb times coulombs, so you get joules left in there. So power, if you remember, is just energy per time. So if we look at that, so that's delta Q times delta V over delta T, or delta Q over delta T times V. And so we realize that that's just current times potential difference, or current times voltage. So that's one of the standard ways to write the equation for electric power. So like if you have a 60-watt light bulb, the amount of current going through it multiplied by the voltage change gives you that 60 watts of power. And it's the same thing as we've had before. Watts are joules per second, and that gives us watts. It's interesting, if you do a little bit of dimensional analysis, you see that amps times volts equals watts as well. So coulombs per second times joules per coulomb is joules per second, which is watts. And then if we combine that with Ohm's law, you can actually write the power equation three different ways. You can just kind of substitute delta V in and get power is I squared R, because you have I times IR, so I squared R. Or you solve for current and get rid of that and get that current is voltage over resistance, and then you get the power is voltage squared divided by resistance. Now when we look at that, so power itself is a pretty easy thing to calculate. So we have two sets of equations we can use there. But where this becomes practical is if you've ever gone outside and looked at your meter coming into your house. You may be home, you may be able to look at it. It's probably your power consumption at home over the past week or so has probably been a lot higher because more people have been home during the day. At least that's been the case at my house. And a lot more devices running, the internet working a lot harder, doing all those types of things, lights on more. But the power bill, that runs what are called, it doesn't measure you in joules, it actually measures what are called kilowatt hours. Kilowatt hours is just actually a measure of energy. So basically, coming into your house, there's a certain amount of voltage that's always being supplied, and then they measure the current, and then so it can do a maximum of 15 amps on this example. If you go out and look at your meter right outside your house, you can kind of probably see something similar to this. This is an older one, an analog version where there's actually a disk that spun. Now it's just all digital outputs, and you can never believe it. They're probably trying to cheat. Just kidding. But basically what it does is it multiplies voltage times current, and that gives you the power, and then it just multiplies by time to give you the energy. And so it's looking at that. And these old ones had the meter basically was kind of like an odometer. You just had a thing that spun around here, and then when this spun once, this increased by 1, and then this spun once, this increased by 1, and when this spun once, this increased by 1. And so they would measure how much that changed each month to calculate your bill. But joules are such a small unit, so you could also call those watt seconds. The power company does what are called kilowatt hours. So it's just the idea that energy is power times time. You put power in kilowatts, and then you put the time in hours, and that gives you 1 kilowatt hour, which is 3.6 million joules. And so your power company then says, all right, each kilowatt hour is 10 cents or 20 cents or 50 cents or however much it's going to be at that given amount of time, and that tells you how expensive your bill is going to be. And so we'll talk about this a little bit later. Your lab for this first part of Unit 11 is actually looking at some of the appliances you use, whether that's a computer or a fridge or an Xbox or a TV or the lights in your room, any of those types of things, and you're going to estimate how much it costs to run those materials.